welcome back to the physics class. In the previous class, we already started our second chapter, okay, and we studied that due to the flow of electric current through a conductor, they produces a magnetic field, and the direction of magnetic field is produced opposite to the direction of the flow of current. And also, we learned about the right hand thumb rule by James Clerk Maxwell, okay. And today we are going to learn about the magnetic field due to a current in a circular coil. So let's start. Magnetic field due to a current in a circular coil can be understood by the following activity, okay. First, take a drawing board and fix a white paper sheet over it. Make two holes A and B in the drawing board and pass a thick copper coil through it. We know copper is a good conductor of electricity and it has low resistance. Connect the ends of the copper coil to a dry cell, that's a normal battery, through a switch and a variable resistance. Close the circuit and plot magnetic lines of force with the help of plotting needle, that is a magnetic needle. Okay, with the help of magnetic needle, we can find out the magnetic lines of force around the conductor, okay, and also we can find out the poles of a magnet. We can see that magnetic lines of force around the hole at A are in anti-clockwise direction, okay, that you can see on this video. However, the magnetic lines of force near the center of the coil become almost parallel, okay. And around the hole at B, the lines of force are in clockwise direction, okay. In the above activity, the lines of force enter the coil from the side of the experimenter, okay. So, we can say that the face of the coil towards the experimenter act as south pole and the face opposite to the experimenter act as north pole. Okay. Now, relate the above observation to the flow of current in the coil, and then we can say that if the current flows in the coil in clockwise direction facing the experimenter, then that face of the coil will act as south pole. Okay. So, this is the motion of current in clockwise direction. Okay. If the current flows in the coil in anti-clockwise direction as in the video facing the experimenter, then that face of coil will act as north pole. Okay. Once more, if the current flows in clockwise direction, it acts as south pole, and in anti-clockwise direction, it acts as north pole. Okay. Next, we are going to study about the conducting wires having more than one turn. We already studied about the conducting coil having only one turn of coil and how the magnetic field lines produced in that coil. Okay. Here we can see the conducting wire is wound into so many number of turns, and here the current flows through each turn of the coil. Current flows through each turn of the coil. And do you know what is the name of this shape? The name of this conducting coil is solenoid. Okay. Next, we are going to study about magnetic field in a solenoid. So, do you know what is a solenoid? Solenoid, it is an insulated copper coil wound around some cylindrical cardboard or plastic tube such that the length of the coil is greater than its diameter. Okay, that you can see on this video. Then it behaves like a magnet when an electric current flows through it. This structure is called a solenoid. In simple words, solenoid is a conducting coil wound in the shape of a spring. So, let's take a look on this figure. When an electric current is made to flow through it, then each turn of the coil behaves like a magnet. In this figure, you can see current is flowing into the coil in clockwise direction. So, the left hand side of each turn of the coil acts as south pole, whereas the right hand side of each turn of the coil acts as north pole. We can change the polarity of the solenoid by reversing the direction of current, that you can see in the second figure. In the second figure B, current is flowing in the anti-clockwise direction. So, the left hand side of each turn of the coil acts as north pole, whereas right hand side of each turn of the coil acts as south pole. Okay. So, listen to the video carefully. Thus, the situation becomes similar to a number of small bar magnets placed end to end with their opposite poles facing each other. That is, a solenoid is equal to a bar magnet such that they collectively act as a bar magnet. Thus, a solenoid behaves like a bar magnet. So, it is clear that if the number of turns in a solenoid increases, then the magnetic effect also increases. And if the number of turns in a solenoid decreases, the magnetic effect decreases. The magnetic field around the solenoid is similar to the magnetic field around a bar magnet. Okay. So, that's about the solenoid. Let me believe that you all understood the topic. Don't forget to go through the textbook. Okay. If you have any doubts, you can ask me through the WhatsApp. Thank you for watching. See you in the next video.